Good afternoon. Today we are going to do a lesson on completing the square. Completing the square is a pretty cool little technique that turns any quadratic equation into a perfect square trinomial. And turning it into a perfect square trinomial is handy because it allows us to take an equation written in standard form and rewrite it in vertex form. And as we have learned, vertex gives us different kinds of information about horizontal transformations, vertical transformations, stretches, and compressions that we can't tell by just looking at a standard form of a quadratic equation. So that is the goal of today's lesson. There are some interesting things that we need to know in order to do completing the square. The first thing is that we are going to take just the standard form of a quadratic equation, and we're going to work a little bit of magic, specifically this 1/2 b squared, or b divided by 2 squared. If we add this to an x squared plus a bx in a standard form, so x squared plus 4x plus some magic number, will give us a perfect square trinomial that can be written as x plus my b value divided by 2 quantity squared. So this is a pretty cool way to write our equations as squares, binomials that are being squared. And that's convenient, folks, for a couple of reasons. A, because now I can see that what the horizontal transformation is, but also later, if I choose to solve this using square roots, I could just take the square root of a perfect square trinomial and it leaves me with just a binomial. So those are just some general reasons we like to use completing the square. The first thing I like to do is practice just figuring out what's the number that's going to turn my quadratic into a perfect square trinomial. So the formula that we have for doing that is this little guy right here, and I'm going to put a star next to him. He's pretty handy. You can think of it as b divided by 2, or 1/2 b quantity squared. I like 1/2 b because I find that most everyone that I have ever met is exceptionally good at taking half of something. That's a mental math calculation that you can do at rapid speed. And sometimes thinking of it as dividing by 2 actually slows us down a little bit, but you can choose to do whichever one you want. So the first thing I like to do is identify what are the parts of my quadratic equation, the a, b, and c, that we learned when doing quadratic formula and when working with standard form, et cetera, et cetera. So the a value here is just a 1. My b value in this case is a 6. And then my c value, we don't know what the magic number is that we're going to put here. I'll give you an analogy in a minute, but this is going to be a magic number that turns this into a perfect square trinomial. So to find that perfect number, we're going to take half of 6, which in this case is 3, and then we square that 3, and that's going to give us 9. Most of you could do this in your head. Half of 6 is 3, 3 squared is 9, and you come up with it much faster than I do. So that is what we add to x squared plus 6x, and that makes this a perfect square trinomial. You probably have written it this way in the past, but because it's exactly the same, right? 3x plus 3x gives me the 6x, 3 times 3 gives me the 9. Because it's exactly the same, two binomials, then I could write that as one binomial quantity squared. And this is the magic that we're trying to get to. All right, so let's just practice that for a few minutes, or for a few examples. In this case, my b value is equal to -8. So if I do my little magic and I take half of -8, and then I take this whole thing and square it, well, half of -8 is -4. And if I square -4, that gives me 16. So 16 is my c value. And I can add it to both sides of this original trinomial minus 8x, and I'm going to add 16. And what you'll find is because we're squaring whatever the half of the b term was, when we do this, we will always be adding a number. This will never be a subtraction sign. And because this is now a perfect square trinomial, I could write it as x minus 4 times x minus 4, and your favorite factoring method will give you this. But because the two binomials are exactly the same, I can write it as a perfect square trinomial. So bad, I hope. In this particular case, for this one, my b value is 30. Half of 30, geez, I can write half of 30 equals 15, and 15 squared is going to give me 225. So I'm going to add 225, that's my c value. I'm going to add that to the trinomial x squared plus 30x. And instead of c, I'm going to put plus 225. And that's wonderful because I take this 15, and that is my perfect square trinomial. You might ask yourself, Ms. Palmer, why do we even bother squaring this number if that's what we're going to use here? And I'll show you in a couple of minutes why we need to also know what the actual c value is. But you'll notice it's handy to have the b divided by 2 because that's the part that goes into your binomial. All right, last one. In this case, b is equal to negative 13. This one's a little cantankerous, so stay with me for a minute. B divided by 2 would be negative 13 divided by 2. And then I would square this to get my c value. And I'm going to square both parts. Negative 13 squared is 169, and 2 squared is 4. Notice, if you could see it, this is a fraction. That's okay. I'm not going to try to write this in decimal form because I suspect it's non-terminating. But this is what I'm going to add to to make my perfect square trinomial. And it's okay to have a fraction here. So my trinomial now looks like minus 13x plus 169 divided by 4. I can still write it as a binomial, x minus 13 over 2 quantity squared. So even though it isn't the prettiest whole number you've ever seen, it still completely works. So that's how we create perfect square trinomials. Let's see how we can use that to complete the square. All right, we're going to do example 2. We're going to write x squared minus 6x plus 12 equals 19 in vertex form by completing the square. So you'll notice this is a full-on quadratic equation. It looks a little different than the ones we were playing with before. It already has a c value. But what I notice is in my original equation, 12 does not make this a perfect square trinomial. He is not the perfect player for my team. This is my analogy that I promised earlier. So I'm actually going to trade him. I'm going to get rid of him. I don't want him on my team. And so what I'm doing by trading him away is I'm freeing up a space to have my perfect player, the perfect number to make my perfect square trinomial. 19 minus 12 will give me 7 on the right-hand side. So now I have space to draft the perfect player. And my perfect player comes from my negative b divided by 2 squared, negative 6 divided by 2, sorry, is negative 3, I'm mumbling, and this comes out to 9. So I'm going to add 9, I'm not going to do it there, I'm going to add 9 down here because I need to add 9 to both sides of the equation, which is why I said earlier we do need to actually know what b divided by 2 squared is because we're going to add it to both sides of our equation here following the golden rule of algebra. So now I have created 16. Now I have created a perfect square trinomial. And I can write that as x minus 3 squared equals 16. So this is, now it's a square. If I were trying to solve, I would take the square root of both sides, but that's a different lesson. For this, the problem is asking me to write it in vertex form. So I can already see that this is a horizontal transformation to the right 3, but because it's not set equal to 0, I'm not 100% sure what the vertical transformation is, but I can figure that out by subtracting 16 from both sides. And now I have x minus 3 squared minus 16 equals 0. And you'll notice that is what vertex form looks like. Once I have it in vertex form, I can say, oh, check it out. My vertex is at positive 3. I almost wrote a negative there. Negative 16, that's my vertex. one of the benefits of Vertex Form, I know that my horizontal transformation, it was to the right 3. I know that my vertical transformation was down 16. I can tell you that my axis of symmetry is at x equals 3. So by putting it in Vertex Form, I have a lot of good information. I can even tell you that right here, there's no a value that's been written in front of my quadratic, which tells me there that the horizontal, or the vertical stretch or compression is just 1. So there's not really one of those going on. So that's how we use completing the square to write something in Vertex Form. Let's take it a step further. Okay, example 3 is asking us to do the same thing that we just did in example 2, but it's a little bit more aggressive. It has 2 extra steps, which I'm going to identify. I'm just going to put a star next to them because these are the steps that are a little bit different from previously. What I noticed when looking at this quadratic equation is that it's already in standard form, which is a bonus, but I also noticed that the leading coefficient is 4, which it was not when I was doing completing the square in our previous examples, and all of these numbers are divisible by 4. It turns out that for our purposes, we want to use completing the square when the leading coefficient is 1, right? So mercifully, this is all divisible by 4, so we're going to have a lot of really gross fractions to deal with. Over here, I'm going to put that my GCF is 4, and we're going to use that again later. And the nice thing about doing that, aside from the fact that now my leading coefficient is 1, is that my numbers are just easier to manage when they're smaller. So now I have my quadratic, and I'm ready to write it as a perfect square trinomial, but -3 is not the perfect player. So I need to trade him to the other side, get rid of him, so that I can free up a space on my team for the perfect player, the perfect number to make this a trinomial. And I calculate that, remember, by saying, well, my b value is equal to -10. So I'm going to take -10, divide it by 2, and square it. -10 divided, that's a 10, sorry folks. -10 divided by 2 is -5, and -5 when squared is 25. So I'm going to add 25 to both sides of my equation, giving me over here a perfect square trinomial. Don't forget the x. Right? He's a perfect square trinomial, and I can now write him as x minus 5 quantity squared equals 28. Okay, well, we learned on the last page, in the last example, that to write it in Vertex form, I need to jack this 28 back over to the other side. So I'm almost done. This is where we stopped on the previous example. But because we factored out that greatest common factor earlier, I need to multiply that back in now. So I'm going to multiply this whole thing by 4, right? The whole thing is going to be multiplied by 4. And here, because I'm trying to go to Vertex form, and guys, this 4 is going to represent my vertical stretch, in this case, because it's a number greater than 0. This is a number greater than 1. Vertical stretch by 4. So I'm going to write it like that. And then I'm going to multiply 4 times -28 so that I can see what the real vertical transformation is. And it turns out that's -112. And 4 times 0 is just 0. So now I officially have it in Vertex form, and I've included my vertical stretch. Next thing we're going to do is we're just going to formally identify a lot of these pieces. All right, so my vertex is at +5, because remember, insiders lie, +5, and my vertical translation is down 112. which is a big number, but curiously, if you will throw this equation into Desmos and then throw the original equation into Desmos, you'll notice that you only see one graph on the coordinate plane, and that's because they're both on top of each other. They're exactly the same. Here's my vertex. My axis of symmetry, if you remember, is always at my x value. So my axis of symmetry is going to be at x equals positive 5. I don't know where that negative came from. My horizontal transformation, because this is positive, means that I'm going to go left 5, insiders lie. It is because my, where did it go? Because my vertical stretch, my a value is greater than 0, a equals 4, which is greater than 0. So it's going to go up like a cup. That is a horrible example of a parabola. It goes up. So my vertex is a minimum. It is the lowest point on my graph. My vertical transformation is going to be down a whopping 112. And I'll go ahead and write domain here for consistency. Our domain is negative infinity to infinity. Look, I'm shedding eyelashes. But our range value is gated by our vertical translation. So the lowest point on my graph, the smallest it will ever be, is negative 112, but because it opens upward, it is going to go up forever. And so we have taken a pretty ugly quadratic. We completed the square so that we could write it in vertex form, and we factored out the GCF. We remembered to put it in as a vertical stretch, and then we identified all the key components of that quadratic. I urge you to pause the video and try example 4 on your own. I am going to do likewise, and then I'm going to cut to the chase and show you the worked out problem. Try it now. All right, folks, here's what I came up with. I factored out a 3, as that is the GCF of 3x squared plus 30x plus 27. I was left with x squared plus 10x plus 9. 9 is not the perfect square trinomial here, so I traded the 9 to another team, and I drafted 25 because I calculated that 25 was the perfect player to make this a perfect square trinomial. I was able to rewrite it as 2 binomials when factored, and because the binomials are the same, I can write it as a perfect square. I invited 16 to come back because I needed this equation in vertex form. And then lastly, I remembered to multiply everything in the entire equation by my GCF, returning the vertical stretch and remembering to distribute that to my vertical translation. So my function 3 times quantity x plus 5 squared minus 48 is equivalent to the original standard form equation, and you can throw them in Desmos and see that they're the same. I could identify the vertex, the horizontal, and the vertical transformation, my axis of symmetry. It is a vertical stretch by 3. My bad, I should have written that the vertical stretch before I list out the vertical translation, but I forgot. My domain is negative infinity to infinity, and because my a value is positive, greater than 0, then my parabola opens up, and the range represents the bottom of my graph. It's a minimum, and so my range is from negative 48 upward to infinity. And that's it, folks. That's how we do completing the square. Hope you enjoyed the lesson. I'll see you soon.